Wow. It's always tough kind of doing an afternoon session because everybody's kind of tired from like hearing like 100 talks. So I'm going to try to bring a lot of energy today and keep everybody awake and excited. I'm really particularly excited to come to Jeju today. So I didn't know about Jeju before this conference. And my friends told me that it is incredibly famous because of all the Korean dramas. So, so it's definitely have to show off on my Facebook page today. So cool. So today we're going to talk about plasma and gaming. And I kind of want to give everybody kind of a background about why gaming on the blockchain makes a lot of sense. If you saw the talk before, the previous speaker actually gave a lot of kind of good information about gaming, but I want to go deep into like all the great use cases for gaming on the blockchain. I want to introduce you to what plasma is and why it's a good scaling solution for Ethereum. And I want to tell you about how plasma actually works. So you've probably heard a lot about plasma. You've probably heard about rainbows and dancing unicorns, and it's the magical solution to everything. And I just want to demystify that a little bit and show you kind of really kind of gritty stuff about what are the actual internals of plasma. Cool. Awesome. So this talk actually starts not today, but 20 years ago. When I was a kid, we used to play these battle card games. And kind of the really popular ones back in America were like Pokemon and Yu-Gi-Oh! And Magic the Gathering. Did anybody here ever play card games as a kid, like battle card games? There's a couple people. Oh, had to wait for the translation. So about 15 people. Cool. So we used to love playing these games with our friends. We used to collect the cards, and my entire childhood was like around collecting these cards. Like my mom's dismay that all of my allowance money would go to buying these cards. So kind of when we grew up as adults, we said, wouldn't it be really awesome if we took those kind of old classic card games and made true ownership of the cards on the blockchain? But wouldn't it also be awesome if we ran the entire game on the blockchain instead of just putting the cards on the blockchain? And at the time, it was kind of a crazy idea. Ethereum really couldn't scale to those levels. None of the other chains really could either, so we started to delve into all the different technology choices that could actually make this possible. So we started building this game. It's a mobile and desktop game called Zombie Battleground. And it's like Magic the Gathering or Pokemon, and you can literally battle your friends on your phone on the blockchain. And the talk today is going to be about kind of the journey we had trying to build this game and build the underlying tech to actually make this game work. Like the tech wasn't even available when we started this game. So we were like building the client and the tech at the same time. So it was a very interesting journey. So cool. So you're probably asking yourself, you're like, why do I need it on the blockchain? I already have tons of games. I play Hearthstone, I play Yu-Gi-Oh!, I play all these games on my mobile phone. I don't care about the blockchain. Well, so let's talk about what are some of the benefits. So what's kind of interesting is right now the most popular card game is this game called Hearthstone. Well, they introduced a new set of cards that completely changed the dynamic of the game. Totally broke how the game was played. And people were just really upset. And there was literally nothing they could do because all of the code and all of the cards were on centralized servers that Blizzard controlled. So I probably shouldn't speak negatively because I know Blizzard is very popular here in Korea. But we're at a blockchain conference, so hopefully I'm a bit safe on that front. But if this is always weird because of the delayed translation, so I have to watch for the feedback here. So if that Hearthstone was actually running on the blockchain, a bunch of players in Southeast Asia could say, you know what? We're not playing by those rules, Blizzard. We're going to fork the game. We're going to host our own servers, and we're going to set up our own block producers that run the game. And that would have been amazing. And then all of a sudden, these game companies would actually like think about the rules, and we could have new games. We could have new evolutions of games. Like, people could fork a game and come up with new rule sets. They could upload new cards, and there's nothing that would need the intervention of the original authoring game company. So that's kind of the core motivation that I have. I played a lot of MMORPGs also. And there's lots of breaking changes in MMORPGs. And right now, that's not possible on the blockchain. But I think that is also something that I really want to see in the future is one day, I want to see World of Warcraft on the blockchain, and we can fork it, and we can just run our own servers. And we can say, you know what? I want that World of Warcraft from last year or from 2 years ago. I don't want today's version. So you're like, Matt, okay, that's fine. That sounds really wonderful. It's going to be open source and amazing. But who's going to pay for this? And why would a game developer that's making all this money want to ever do this? Well, of course, the answer is no, they wouldn't. Somebody like Ubisoft or Blizzard or Activision, they're not going to want to do this. But there's a whole generation of upstart game companies that want to build games, and they need a way to monetize. They need a way to fund their game. So, I mean, sure, there are publishers, but there isn't quite as much venture capital for games. But what we're seeing is there's a new venture capital for games by selling initial items in the game on the blockchain. And we did this for our game, and we sold hundreds and hundreds of thousands of dollars of game items before the game was launched. And this is a really amazing way for indie game developers to fund their games, and that would give them the motivation to build their initial game on the blockchain just by the funding and the monetization mechanisms that the blockchain give. What's also cool is for the players can trade their cards. They own them. So if I want to sell my cards to another player, I can sell them on any distributed exchange. So we've now given true ownership to the players, and we've taken power away from the game companies themselves. So obviously, we're not the first people to talk about blockchain games. This has actually been going on for about 5 or 6 years now. As far as I can tell, one of the first groups to do this was XCP or Counterparty. And they built virtual items on top of Bitcoin. And you could make cards, or you could make little figurines, and then you could create virtual items on top of Bitcoin and then trade them with your friends. And this wasn't ever very big. Most of the people here probably have never used this or looked at this, but it's been going on for quite some time. And you're wondering, well, if it's been around for 5, 6 years, why has it not gotten more popular? Well, it wasn't really until Ethereum broke on the scene. And Ethereum was kind of the game-changing blockchain, right? And I'm sure most of the people here know, although I did meet quite a bit of EOS people, is that Ethereum was kind of one of the first blockchains to really have smart contracts on the blockchain. And with the smart contracts, all of a sudden now we can have non-fungible tokens. We could actually execute some of the game code on the blockchain. Whereas with Bitcoin, we could have some of the assets, but we could never have the logic. We couldn't actually have our Pokemon attack another Pokemon. We couldn't have our cards merge and create new cards. We couldn't do anything interesting with the actual assets on the blockchain. So before, and then this game came out. How many here played CryptoKitties or used it or know about it? All right, more than half the audience. This is probably the only blockchain application outside of Bitcoin that has actual mainstream people using it, right? And it was huge, right? And if you look at CryptoKitties, it was such a basic game. All you could do was buy, sell, breed, and trade your cats. It was really just kind of a gambling simulator for trading cats. And that was kind of its appeal. But that's all you could do on Ethereum, right? Because we know proof-of-work networks are still quite slow. So they didn't have a lot of ability to build like a real game on top of it. So kind of like we know Bitcoin and Ethereum are these proof-of-work networks, right? And the proof-of-work networks are maybe getting around 10 transactions per second. But they're incredibly secure. We can trust them with everything that we have, and we can know that nobody's ever going to steal our assets. But at the same time, they don't do very well for actually doing lots of smart contracts or doing lots of interesting operations. That's where delegated proof of stake is starting to come onto the scene. And you're starting to see a lot of new blockchains that are very oriented around delegated proof of stake. So you have EOS, you have us at Loom Network. I believe Neo is DPoS. And now, all of a sudden, you have something that is a lot less secure, but all of a sudden has tons of transactions. You could be doing hundreds or thousands of transactions a second while still having some level of security. And all of a sudden, DPoS has now opened up that we could actually build a real card game that we showed earlier. And this is where I think, and I'm gonna, and my goal today here is to sell sidechains as part of the Plasma, is that layer 2 sidechains are going to be the future scalability solution of blockchains. And let me tell you why. So you have a mainnet like EOS, and you have a mainnet like Bitcoin. Well, the thing is, with something like EOS, you have 21 people that can potentially collude, right? Whereas Bitcoin, no amount of people can collude. So you can always trust Bitcoin. But if we can actually pair a DPoS network like Ethereum, or like EOS or like Loom, with a proof-of-work chain like Ethereum or Bitcoin, then we could actually have a very high scalability solution for in-game transactions. But then we could have a very safe solution for the items that actually exist in the game. And the real complication, and one of the biggest problems that why this has not been happening, is there's not been a great mechanism for moving the assets between the two blockchains. So I spoke before that like the old games were CryptoKitties. And now we have something, this is our zombie battleground game, which is on alpha right now. You can run it on a mobile device. And it is a full battle card game, and literally every single transaction runs on the blockchain, on our layer 2 DPoS chain, which was just not possible before, and it blows away anything that something like a CryptoKitties could have. And one of the first initial problems that we had with this game was, okay, so we have the game logic running on a sidechain, but we want to mint cards for the players. So as part of our initial sale, we had minted 2 million cards. So I don't know if you've ever tried to transfer 2 million individual objects on Ethereum, but we would have basically clogged all of the transactions for like a week on the entire network. So obviously, this wasn't going to be possible. But we wanted to find a way of being able to secure these assets or transfer these assets while still minting all of them. So these are the kind of cards. So this is just like any other kind of card game. And these are getting minted on Ethereum mainnet. So right now, there's 2 million of these on Ethereum mainnet. And we wanted to secure it. So that's when we ended up looking at Plasma. So that was kind of the backstory. I kind of wanted to give you guys the reasoning we got to the point where we wanted to build out Plasma and why we needed to use Plasma. Now I'm going to kind of go into what is Plasma and how it works and how it actually solves these problems that I was talking about. So just really quick, I just have a 10-second slide about me. So I run Loom Network. We do scalable sidechains. I'm a big Go developer, so if you guys want to geek out and talk about Go language, you should come talk to me after the talk. And just a fun fact about me, or 2 fun facts. I rode an elephant into my wedding, which, although what the TV tells you is actually not traditional in Thailand, and if you get me drunk, I love speaking Thai. So this audience probably not so relevant, but it's always kind of a fun thing for me. Cool. So I want to start with what was plasma. First off, has anybody here actually heard of plasma in any capacity at all? Okay, so like about half of the audience has at least heard plasma. Probably heard it on Reddit posts, and they're like, plasma's going to make Ethereum great. You should go buy lots of tokens. That's probably what you heard, so it's true. Not just kidding. So plasma originally started at a white paper from Vitalik last year. And if you read the white paper, you could kind of conclude that plasma was not possible. Plasma originally was supposed to be, we can run whole EVMs, whole virtual machines in a sidechain, verify all the transactions through Merkle proofs, and then submit the Merkle proofs back to the mainnet and verify them. So we could have these magical subchains that would just appear and disappear at will and be able to be infinitely scalable. Well, when I originally read that, I was not convinced. And it didn't end up happening. And that plasma was kind of thrown away. So like, if you've ever read the white paper for plasma, that is no longer what plasma is. Plasma has really changed dramatically. Plasma today is more like a payments channel. So if you can think of Lightning for Bitcoin, or even like Raiden, where you can take payments or even non-fungible tokens from mainnet, you can transfer them to a sidechain, you can trade them, you can transfer them to many users thousands and thousands of times, and then you can bring them back to mainnet with very little costs. So that's kind of the main thing that Plasma does. If you want to think of it in one sentence, Plasma allows assets to be transferred and traded on a sidechain with virtually no cost. And when the transactions are done, they're committed back to the mainnet, in this case being Ethereum. There's two parts that actually make that happen. So you actually deploy a Solidity smart contract onto the Ethereum mainnet. Then you have a secondary sidechain, sometimes referred to as a plasma chain. And when users want to trade, they are depositing their assets into the smart contract on mainnet, and then they appear on this plasma chain. And we're going to go into this in more detail, but that's kind of like the very high-level overview. So if you've been reading online, you're probably incredibly confused by Plasma. There's like Plasma Cash, there's Plasma XT, there's Plasma Debit, there's Plasma MVP, there's like Plasma this, Plasma that. So basically what's happening is there's lots and lots of working groups in the Ethereum community that are making their own versions of Plasma. And there's lots and lots of little different standards. And it's really good, so there's lots and lots of innovation happening, but it's very confusing if you're sitting from the outside. But for the sake of this presentation and the sake of easiness, unless you are a mathematical researcher and you're interested, for all practical purposes, Plasma Cash is the real Plasma. This is the stuff that's kind of ready to go to production. There's several implementations. Loom, our company, has one. BankX and Omise Go all have implementations of Plasma Cash. And this is like, if you want to look at Plasma today, you should start with Plasma Cash. So it's kind of funny because originally I had written off Plasma. I didn't think that it was a real solution. I didn't really believe in it. But then one day I get a message on Reddit from some random dude called The Buterin. And he's like, oh, you Loom Network guys should really check out Plasma. And I was like, who is this? Oh, and I was like, oh, shit, it's Vitalik. And he's like, yeah, let me introduce you to the Omise Go guys. They're down in Bangkok, too. You guys should meet up. They'll tell you all about Plasma. So we all got together at a coffee shop in Bangkok, and they're telling me about this Plasma Cash thing, which I had not really heard anything about. And I was sold. And in 30 minutes, I changed the entire direction of our company. I was like, that's it. I know that Plasma is the next big thing. So that was kind of an amazing revelation to us, and I guess I have to thank Vitalik for kind of pushing me in that direction. So just kind of about us and about like how we started and how we kind of moved in this direction. So Loom Network has this thing called the Loom SDK, and it's essentially an SDK for doing layer 2 sidechains. So if you want to build a Dapp, let's say that you have a very popular Dapp, like a CryptoKitties or, for example, Axie Infinity, and you want to move your game onto a sidechain. We have an SDK that quickly lets you do that. It has a full DPoS implementation, and now we have Plasma Cache support on the sidechain. And you can kind of think of it, we kind of coined it as EOS for Ethereum. And we were originally just going to do the DPoS sidechain, but now we're kind of very convinced that Plasma Cache is the future. So how does Plasma actually fit in? What is the diagram? And you're probably looking at this diagram and you're like, oh my god, my head's about to explode here. So we're going to walk it through, and I got about 12 slides to like explain this diagram, so don't worry, you're not gonna die. So basically, the general idea is that at the very top, we have a plasma chain. And users that are interacting with that plasma chain are actually sending transactions to it. So like, let's say that I have a CryptoKitty and I want to give a CryptoKitty to this guy, and then he trades it to that guy and that guy and that guy. And then eventually, somebody wants to get that CryptoKitty back on Ethereum mainnet. What's happening is every time we're doing transactions on this sidechain, the sidechain is actually creating Merkle proofs and a Merkle tree and these things called plasma blocks. And every so often, it will actually write one of these Merkle blocks into a smart contract on Ethereum. So there's literally a smart contract that is tracking all of the transactions that are happening on the sidechain. And you say, how could that be efficient? So basically, for every single block on the sidechain, we can have up to 65,000 transactions. So you can compress 65,000 transactions into one transaction on Ethereum mainnet. So you can get this massive compression of transactions on the sidechain. And then what's also happening is you have this smart contract on mainnet that is actually tracking the security of these transactions. And when the user that we talked about before wants to get his CryptoKitty back out onto mainnet, he goes to the contract and he says, oh, I want that CryptoKitty. And they're like, well, do you have proof? Do you have Merkle proofs that you did it? So he submits these Merkle proofs. And then there's a period where other people can say, oh, no, that guy's cheating. So it's pretty cool. And we're gonna delve into each bit of this. So this is kind of like a stick figure diagram. I know it's kind of ugly. I wanted to have a quick one. But it's really simple from a user's perspective. Realistically, the client of Plasma is interacting with two things. It interacts with a smart contract on Ethereum, so that's all incredibly standard. And then it has an interaction with the Plasma chain. And it just is basically sending transactions to these two chains. And it's kind of happening invisibly to the end user. And I'm going to show in some later slides what that actually looks like to an end user. So first thing, let's talk about deposits. So imagine that I have a bunch of ETH on mainnet that I want to transfer, and I want to transact with a dozen other people. I would deposit all of my ETH, or whatever the ETH that I want to use, into this smart contract. And this smart contract is going to give me a Plasma Cache identifier. And then from then on, I can submit this Plasma Cache identifier onto the side chain, or the Plasma chain, and then I can use it for creating transactions on the side chain. So what does that look like? So imagine Alice, she deposits 5 ETH onto the smart contract on mainnet. Then that 5 ETH is automatically being put into the plasma chain. So the plasma chain is actually monitoring Ethereum mainnet. But Alice is also keeping track of her transaction history, because Alice has to keep proofs, and the end user doesn't have to do this, but in the client software, it's actually keeping proofs of where the transaction history actually came from. So let's say that on block 1, Alice had deposited this 5 ETH. And now on block 2, on the plasma chain, she wants to transfer it to Bob. So she transfers that 5 ETH to Bob. Well, now on block 3, neither of them are doing anything, right? So block 3, maybe these two guys over here are doing transfers between each other. And now on block 4, all of a sudden, Bob needs to transfer this to Charlie. But he can't just transfer it. He has to transfer it, and he has to give proof that he got that from Alice. And he has to keep a history. And what's happening is, as the coin is moving between person to person, the entire history of all the transactions of that coin are actually moving with the coin. And that's how the end person is proving that they actually have the ownership of this token. You're like, wow, this sounds really complicated. But the end user doesn't have to care. So like our JavaScript library, for example, just does this automatically. And nobody, like even you as an end developer, don't have to know how to manage tracking these proofs, because the Plasma Cash libraries themselves actually are tracking these proofs under the hood. And now, let's say that Charlie wants to take this 5 ETH and bring it back to Ethereum, because he wants to go use it somewhere else, right? So he goes back and he goes to the contract on mainnet. And he says, hey, I want to withdraw this 5 ETH. Here's proof that Bob sent this ETH to me. And he sends it to the contract on mainnet. The contract on mainnet's like, OK, that's cool. You need to wait, say, 24 hours to see if anybody is going to contest this transaction. And that period may be a day, it may be a week, it could be some period of time that that contract has established for challenges. So that's what we were talking about with withdrawals. Basically, withdrawals are never immediate. Well, and we'll talk about how withdrawals could potentially be immediate later. But initially, withdrawals are never immediate. So when you withdraw, you have to actually wait for a period of time. That's when challenges come in. OK, so now let's imagine that Charlie was withdrawing that money. And Alice, who gave him the money, tries to cheat the system. And she's like, oh, I didn't give that money to him. So she's trying to double spend, right? Because she gave it to somebody else, but then she says, oh, no, I still have it. And that's when a challenge comes in place. And the challenge, if you take away anything about Plasma Cash, all of the technology for doing these kind of transfers, all of the problems is in the challenge. If anybody tells you they have a solution to do cross-blockchain transfers and they don't have any kind of challenge conditions, that means that they have not thought this through very hard. This is really the most difficult part about all of this. So basically, and I'm going to put these slides online because this is what we'll go into detail, is basically when you're doing the exit, what you're trying to do is you're trying to validate that somebody is not double spending and that other people can challenge the double spend. So when we're looking at this one, this is kind of back to the other example where we had transferred that coin 3 times, and when we do the exit, we tell them, hey, it had been transferred 3 times. So let's say that we tried to do the double spend. So we had that scenario where Alice had given the coin to Charlie, and then they both try to exit. Well, what happens is both parties have to submit a proof. Alice has to submit a proof that she got the coin originally, and then Charlie has to give a proof that he got the coin. Well, whoever actually has the longest proof history wins, because basically that's why we have to keep the history in sync with each transfer, as we keep track of all the people that that coin history went to. So whoever has the longest coin history is actually the real owner of that coin. And from the outset, that sounds really simple. You're like, oh yeah, obviously it's the person with the longest link. But it's actually really complicated, because the smart contract on Ethereum has to do this. So the smart contract on Ethereum has to keep its own Merkle trees of the plasma chain to validate that these proofs not only do say what they are, but they're valid, because you don't want somebody to be able to generate fake proofs also. So the proofs have to actually match up with the Merkle tree that the contract on mainnet has. And this can also get into other challenges that I'm not going to go deep into, but if you're really interested, is what happens if the plasma chain dies. It's not even cheating, it's just the servers go away and it stops sending data. And you have a data availability problem. There's a lot of really complicated scenarios where you could get into situations where people could try to cheat the system. Yeah, so this kind of goes into what I was saying just a minute ago, was on this slide, somebody actually created a fake proof saying, oh, somebody sent this token to me, but they didn't really send it to him. And that's where we're actually going through the Merkle tree in Solidity. And this was really nasty. So like there's like a very optimized sparse Merkle tree implementation in Solidity to like optimize for gas to be able to even do this. So withdrawals. So basically that kind of, the last part of the withdrawal is that if nobody challenges, or if all the challenges have been seceded, after a period of time, you can call the contract and the contract will give you the money back. So that's kind of the main workflow. I know I kind of went through it quite deeply. I went through it quite fast, but part of the issue here is that like you kind of want to know the general flow of this, but there's two kinds of developers in this. If you're going to be a developer that is going to be using Plasma Cache, you just need to have a kind of an overview and an understanding of like basically how the system works. If you want to build your own Plasma Cache implementation, you'll need a lot deeper talk. And if anybody here is working on a Plasma Cache implementation, please talk to me afterwards. I'd love to kind of give you details. We went through a lot of pain on these things. So kind of a diagram of what we just talked about, just to kind of try to cement what I'm saying, is that there's only 4 states for any data in the Plasma contract. So either the token is deposited, which means once it's deposited, then it can be thousands of transactions can be happening, and there's no other state transition for transactions happening. At some point in time, somebody will do an exit, and that's when they're starting their withdrawal. The first step of a withdrawal is an exit, and an exit can either be challenged or it can just finalize, and that's basically the loop. So we had talked about the first couple slides were on the deposited and all the transactions that were actually happening on the Plasma chain. And then the last 5 slides where we were talking about Alice and Charlie actually trying to cheat the system are the different kinds of exit and challenge conditions. And then in the upper right there will be once it's exited. In our case, on Loom, we like to do a day. I know Amise has set like a week as like the kind of challenge period time that they do. So Merkle trees. I mean, obviously, probably almost everybody in this room knows about Merkle trees. And obviously, Merkle trees are one of the main technologies that are actually making the Plasma Cache efficient enough to happen in a smart contract. What's really kind of cool is, I want to just talk about this, is if you just want to geek out, and you just want to have a really geeky situation is because Solidity is so gas expensive, there's somebody that has a compressed Merkle tree, sparse Merkle tree implementation. You can look at our repo, but we didn't make it. It is unbelievably amazing to look at, and it's probably one of the more interesting pieces of code that I had to deal with. So I'll just throw that out there as kind of a fun, geeky thing if you want to take a look at. And I only have 5 minutes, so I want to show this how it works, and I want to save at least for 1 or 2 questions. So this is actually a copy of the marketplace for our game. And I wanted to show you what a Plasma transaction would look like to an end user. So for example, they're going to buy a card here, right? So they're going to pick a card, and they're like, cool, OK, I'm going to transfer the card to either Ethereum or my wallet or something like that. And right now, then what's going to happen is you're on a mobile device. So what's going to happen is it's going to pop up your wallet software. So for example, we're big fans of Trust Wallet, which is now, I guess, Binance Wallet. And basically what would happen is they would sign the transaction to do the withdrawal on mainnet to the Plasma contract in their wallet software. After the wallet software jumps back, they come back to their screen and they have their thing. So to the end user, the Plasma really isn't that much different than a normal transfer to them. They would just end up signing the Plasma transaction instead of an ETH transaction signing. So just really quick to get started, we have a really cool thing called Crypto Zombies. If you guys haven't learned Solidity yet, you should check out Crypto Zombies. It's a really great way to learn Solidity. And our Plasma Cash repo is open source. So I would suggest taking a look. We have a Korean developer chat room too. So if you want to take a look and you have questions about Plasma Cash, our staff actually translates it, and people in English will respond to you back in Korean. So it's quite nice if you're interested in learning more about that. And I'm kind of low on time, and I wanted to get 1 or 2 questions, so I'm going to leave it for questions right now.
네, thank you, Mr. Campbell. 그러면 바로 Q&A로 넘어가 보도록 하겠습니다.
This is a great question. So the question is, Tendermint and Zilliqa use practical Byzantine fault tolerance for speed. Why use DPoS for seed and scalability? Byzantine fault tolerance and DPoS are not competing technologies. This is very confusing. So if you look at Cosmos, which is built on top of Tendermint, they have DPoS. DPoS is a mechanism for determining the validators in a system. Byzantine fault tolerance is just a system for doing consensus. It has no staking, and it has no way of adding or removing validators. So you need both. Next question.
네, 질문이 하나 더 있는데요.
It seems like Loom is using 3 consensus algorithms: DPoS, Plasma Cash, and Ethereum mainnet. Won't it take longer to do a transaction? It's a great question. Game logic is actually being run on the DPoS consensus system. You're only using Plasma Cash when you're transferring assets to mainnet. Mainnet transfers were already very slow, and now they can be a lot faster because you can trade those assets on the sidechain, and it's only when you go back to mainnet they're slightly slower. So no, the question was, it would not be slower. Next question.